Hello everyone, my name is Lennard and I'm an application engineer at Rigel Medical. This presentation and webinar today has been developed to educate biomedical and clinical engineers, technicians in vital signs and simulation. Firstly, we'll just have a quick overview of our company and what we do. Then we'll take a look at the primary vital signs. So this varies, but we're going to look at 5 of those main vital signs and how they're commonly measured in healthcare settings, and then what we do to test the patient monitoring systems by using vital signs simulation. So we're looking at methods of patient simulation and why it's crucial to test each patient monitoring component. Firstly, a little bit about ourselves at Rigel Medical. We are renowned globally as a designer and manufacturer of reliable, portable and compact biomedical test equipment. Our reputation has emerged from our 38 plus years of experience. Our products ensure that critical medical equipment is safe to use throughout the device's life cycle. As metrology specialists, for almost 4 decades, our innovative testing solutions have been mitigating risk worldwide in healthcare environments. And we've got over 40 distribution partners. That's covering over 110 countries with 7 Rigel authorised global service centres, but we're also expanding upon that. Our manufacturing site and main office is based in Peterlee in the UK, but we've also got a US office which is based in Tampa, Florida. Something a little bit different in today's webinar, we've got a chance to win the PatSim 200. That's quite relevant to our vital signs webinar, so a few of you that are on today may be interested in this particular competition. All you have to do is fill out a form on vital signs simulation, types of simulators and your genuine feedback on what you think about your current patient simulators if you use them. It'll only take a few minutes to do, and after you've got a chance to win a free PatSim 200. So you can either use this QR code here or the link that can be found at the bottom. Once you've filled out that form, you'll be automatically entered into this competition. This slide is available as well in the handout section, so don't worry if you haven't got time to get out your QR code scanning app quick enough. That is available in the handout section, so you'll be able to revisit that and access the form. What's going on there? Okay, so now we'll delve into the webinar. So vital signs consist of 4 to 6 crucial medical signs and are used to communicate a patient's condition and the severity of disease to healthcare clinicians. Any abnormal values outside of these normal ranges excuse me, are crucial in determining clinical deterioration. Recent studies suggest that changes measured in vital signs occur several hours prior to a serious event. So they allow for continuous monitoring of a patient, with medical staff being continuously informed of the changes in the condition of a patient. Modern patient monitors, they warn of pending fatal cardiac conditions before visible signs are noticeable to clinical staff. So this is very crucial in determining a patient's condition before anything becomes obvious, and that's become apparent in COVID-19 how crucial patient monitoring systems have been to clinicians. So in today's presentation, we're just going to talk about 5 of these vital signs, and these are considered to be the primary ones. Sometimes up to 7 that are considered primary, but we're going to talk about these 5 here. Now, blood pressure, there's 2 types of measurements. You've either got non-invasive blood pressure and invasive blood pressure, and we'll come on to why we use 2 different types of measurement. There's oxygen saturation. These measurements are done via pulse oximetry. We've got heart rhythm, so an electrocardiograph, which measures the electrical impulses from the heart rhythm. There's respiratory rate, So ECG lead impedance. So this measure uses two ECG leads and measures the impedance between 2 points. Then there's temperature, typically a thermistor, which is used on patient monitors. There's also other methods of measuring temperature, so infrared, thermocouples. There are also methods of measurement used in healthcare, but we're talking about simulating and measuring on patient monitors where thermistors are primarily used. And we've got the normal range in healthy adults for each of these vital signs, and then any values outside of these ranges alert clinicians to a condition deteriorating that needs to be monitored. So patient monitors, what do? They continuously observe or measure vital signs. Patient monitors are very common but highly complicated devices. It's one of the primary methods of detecting, diagnosing and treating unexpected patient events. They provide physiological input data to directly control connected life support devices. Patient monitoring, there's surges in patient flow and reduction in clinicians with an increase in remote patient monitoring. So with increases in ageing population globally, you've got more patient monitoring being done remotely, so within not so much in healthcare environments. Patients are also being monitored at home in different environments, and this has increased the growth of patient monitoring and central patient monitoring systems. Now with these, up to 64 monitors on one system can be available. Each individual patient monitor must therefore be performing correctly and safely. Now this talks about patient monitoring in healthcare environments. So up to 64, whereby one clinician could be monitoring up to 64 different patient monitors. That highlights furthermore how crucial ensuring that patient monitorers are within specification and that they are performing correctly. And that's really highlighted by the fact that the reduction in clinicians means that it's these pieces of equipment that are monitoring the patient more and more than individual clinicians are. So let's talk about physiology firstly. So vital signs in the physiological aspect. All vital signs are related to the operation and functioning of the respiratory system. The heart circulates blood through the body and lungs, and it's central to the respiratory system, and it can be seen as the main engine within the body. Oxygen attaches to hemoglobin in the red blood cells, reaching the brain tissues and organs in order to sustain life. Acts as two pumps. Oxygenated blood flows from the lungs through the left side of the heart, whilst deoxygenated blood flows from the tissues through the right side of the heart to the lungs for reoxygenation. And so if we look at the diagram, your red circuit is known as systemic circulation, and this is what's from the lungs through the left side of the heart. So this is your oxygenated blood, and the blue circuit is known as pulmonary circulation, and this is what's being performed to reoxygenate the blood. So the blood's gone via the tissues, it's come back to the right side of the heart to be reoxygenated, but it's not going to be reoxygenated until it reaches the lungs and then pumped back through the body. So you've got systemic circulation and then you've got pulmonary circulation. Now, whilst the ECG shows the electrical activity of the human heart, pumping the blood, the oxygenated blood around the arteries, this is where blood pressure is generated. So there's your first two stages related to vital signs. So your ECG is showing your electrical activity from the heart. It's pumping the oxygenated blood around the arteries, and this is what causes your blood pressure. So that's where your blood pressure is monitored. Now, respiration rates, they might show any obstructions. So if your lungs are not performing correctly, so if you've got no, if your breathing is reduced to a point where no respiration is being measured, this is known as apnea, and that of course affects the airways and the way that oxygen is absorbed into the lungs. So there's your third vital sign. And then on top of that, you've got the core body temperature. This is another very commonly measured vital sign. So if you've got poor circulation, then your body temperature might drop. If you've got a fever, then your temperature is going to rise. And these monitors of temperature, very simple form of measurement, but it's really crucial to determining a patient's condition. And that really highlights all of the vital signs, except for SpO2. So SpO2 just monitors how well oxygenated blood is within the body, and it does this by using pulse oximetry, which just monitors the levels of oxygenated blood compared to deoxygenated blood. But we'll come on to that in the measurements section of this webinar. So firstly, we'll talk about the complete cycle of events in the cardiac cycle, or a single heartbeat. This is referred to as the cardiac cycle. So cardiac muscles are electrically stimulated, and the first part of the cardiac cycle is introduced by or triggered by the SA node. So that's also known as your heart's pacemaker. Then through timing and delays, it travels through the AV node, which is the atrioventricular node, and then through to the bundle of His. This ensures that there's coordinated contraction and relaxation of the different heart muscles to allow the chambers to fill up with blood correctly. So each individual chamber of blood needs to fill up correctly, and that's performed via these electrical stimulations. And they've got timing delays which allow for each chamber to fill up correctly. So pressure chambers fill up with blood during the low pressure diastolic phase. Then this is when the heart muscle relaxes. There's build up in the ventricles, provide the required condition to allow circulation. So this is a high pressure or the systolic phase. A complete cardiac cycle of events is referred to as the cardiac cycle. A single heartbeat involves atrial systole, ventricular systole, and complete cardiac diastole. So heart rhythm, electrical impulses cause the muscles to squeeze and pump blood from the heart. The P wave is generated during atrial depolarization. Following this, the right and left ventricles are depolarized, generating the QRS complex. The T wave represents a return to resting rate for the ventricles. And a patient monitoring system measures these tiny electrical signals in millivolts to ensure that the right electrical impulses are being produced. So it's not actually the changes in electrical impulses that cause the problem, it's the physiological effect of what that can do. So if there was a change in the delay between the T wave and the P wave, that's not going to allow enough blood to fill into the ventricles, and you're going to have problems within circulation of blood. And there's all sorts of electrical conditions which affect the heart's ability to pump blood around the body, and we'll come on to that in some of the next few slides. So this is a normal sinus rhythm. We've got our electrical impulse here, and it shows how the electrical impulses flow from the AV node around to the AV node, from the SA node round to the AV node and into the bundle of His. And then you've got your ventricular muscles that contract. This is your R wave peak. So your P wave represents the atrial depolarization, and that's as the electrical impulses reach these bundle fibers. As the right and left ventricles are depolarized, that's what generates this QRS complex, the peak R wave, and the T wave here you can see represents that return to resting rate through the ventricles. So we've got blood pressure. This is the most common vital sign parameter being measured or monitored, and it's arterial blood pressure. In the image it shows the cardiac cycle. So we've got our electrical impulses and where the ventricles contract and how blood pressure is generated after the complete cardiac diastole. The blood pressure is at its lowest diastolic here, and that's your lowest aortic pressure, and that allows blood to circulate through the body through this system, and blood pressure is measured by using systolic diastolic pressures. Now the pressure change with each stage of the cardiac cycle is reported in millimeters of mercury. In a healthy patient, the average values for different pressure variations are systolic pressure 120/80, where mean arterial pressure is 90 to 93, and this is calculated using this calculation here, where mean blood pressure equals 1/3 times the systolic value plus twice the diastolic value, and that's how you reach your mean arterial pressure. So mean arterial pressure across the full cardiac cycle. So systolic, not long after cardiac depolarization, and your lowest aortic pressure is just before, or just after depolarization of the QRS complex. So obviously there's a bit of a delay between your heart contracting and the blood reaching the arteries. So the same image from before shows the delay between the QRS complex and the peak pressure in the ventricles. So you've got the depolarization, and your aortic pressure is reaching peak aortic pressure here. So this is a much slower version of the QRS complex, just to show the different phases during the pressure cycle. Now SpO2, this estimates the amount of oxygen in the arterial blood. Hemoglobin is a protein that carries oxygen in the blood. The measurement is by the percentage of oxygenated hemoglobin compared to the total amount of hemoglobin in the blood. E.g., a value of 95% means that the blood cells are made up of 95% oxygenated and 5% non-oxygenated hemoglobin. Values below 90% indicate low blood oxygenation. Now this image shows how oxygen blood changes to deoxygenated blood as it carries oxygen to the organs and the muscles around the body. Oxygen is absorbed by the blood as it passes through the lungs. As the oxygen sticks to the hemoglobin protein in the red blood cells, then that's then passed around the body. Now the quantity of oxygen absorbed, which is then known as oxyhemoglobin, that's a sign that the body is performing as it should. The respiratory system performance is behaving well. That's why it's such a commonly measured vital sign. If you're getting oxygenated blood via your lungs, and that means that the heart and the lungs are both performing as they should. The cardio-respiratory system is behaving correctly, and if SpO2 values start to reduce, then that's a sign that either the lungs or the heart have stopped performing well. That's again was highlighted within COVID-19. SpO2 monitors were becoming more commonplace. Even the cheap handheld SpO2 ones that were being sold were there as a sign to see how well your lungs were performing. If oxygen wasn't binding to the red blood cells correctly, then it's going to quickly be indicated through the SpO2 or pulse oximeter. So respiration. Now, inspiration of the lungs is a result of the increase in the volume of thoracic cavity, and it's a result of involuntary contraction of the diaphragm. So this is the body's way of bringing air into the lungs. Now, of course, if a patient is under mechanical ventilation, then that pressure is being created by the ventilator itself and not from the patient. But I won't talk too much about ventilators. We've got a presentation on that anyway, a webinar. If you've got any interest in that, sign up to that one. That'll be coming up next year now, but I won't go too much into the principles of ventilators. So the thoracic cavity volume is increased as a result of involuntary contraction of the diaphragm, and this is the layer between the lungs and the abdominal cavity. The intercostal muscles also aid the breathing process by lifting the lower and upper ribs. Expiration of the lungs is a result of the elasticity of the lungs forcing air out when the diaphragm and intercostal muscles relax. Now, elasticity of the lungs is another indication for ventilation. If you've got poor elasticity, if your lungs have become stiff or rigid, then that's another indication that ventilation is required. So there's all sorts of indications for ventilation. Monitoring of the respiration rate on patients subject to anaesthesia is vital as it provides immediate warning of changes to the respiration rates. Now, if a patient's under general anaesthetic, they might lose that ability to sustain the control of the diaphragm and the intercostal muscles. Again, another indication that mechanical ventilation is required to deliver breaths and your respiration. So you'll have set respiratory rates to ensure that you're still getting the same respirations as you would under involuntary control. So there's another indication here for respiration for ventilation. Then we've got temperature. Again, this is one of the most monitored vital signs. You've got several devices which monitor and measure temperature over the years. So you've got things like mercury field thermometers, though of course they're no longer available due to the toxicity. There's resistor-based sensors, and even to your non-contact infrared-based temperature sensors, which have become much more commonplace again since COVID-19. Now these are not just in healthcare environments. You've seen these at all types of events, sports centres. They use them all over the country, all over the world, as a form of a quick measurement of your internal body temperature. And the average core body temperature is 37 degrees plus or minus 0.5, and this can vary by gender and between different stages of the day. Now I've tested this myself. If I've got up very early in the morning, my temperature is really low, it's below 36, and it starts to rise throughout the day. Thermoregulation ensures a constant internal temperature or homeostasis, and it's crucial in survival. Elevated temperature is common during infection. Reduced temperature is caused by external environments or patient's illness. Treating excessive temperature variations is important in preventing fatalities. Oh, and then also the diagram on the right. If you've got an excessive low temperature below the normal range, is known as hypothermia, and if you've got an excessive high temperature, this is known as hypothermia. So outside of the normal ranges to clinical conditions. Patient monitors. So a monitor is defined as a device that measures and controls performance. Patient monitors observe and measure vital signs continuously and provide warnings in the case of a serious event. Monitors or monitoring systems alert clinical staff of anomalous vital sign values and to some extent control the life support devices. So these comprehensive monitors are widespread. They're globally used in healthcare facilities. You'd be hard pressed to find a healthcare facility that doesn't use patient monitors. They are, they're absolutely everywhere. And something that sometimes is not as clear, which is why we highlight, is a monitor is defined as a device that measures and controls of performance. Sometimes which can be misconstrued is that monitors actually just measure. They're used to measure conditions, but they are there to control performance as well. So that's becoming more and more commonplace for patient monitors, modern patient monitors, really comprehensive devices. So each individual function. Patient monitors are capable of transducing signals from many different types of sensors to a display in a format that can be read or recorded. They're therefore classed as multi-parameter devices. Patient monitor needs an electrical signal to display a reading, so we need to look at how each vital sign is transduced. So these images show the various transducers, and they provide a simplified schematic of how signals are converted. So not necessarily, the measurement principles are not necessarily complex. Once you start to establish what patient monitors are doing, we can work out how to perform patient simulation. So in the top left image, this is a IBP transducer where the pressure is converted into voltage by changing the resistance of a strain gauge within this Wheatstone bridge circuit. So if you're familiar with electronics, would have seen this on many occasions, how the resistance of a strain gauge within a Wheatstone bridge will change the voltage. And that's how IBP is measured. So you're measuring direct pressure via this, typically it's a fluid filled catheter, and that changes the pressure. It's a fairly simple way of measuring pressures. The image in the top right represents SpO2. This is where light from LEDs are absorbed by the different types of hemoglobin, and they're detected at a photodiode. So use different wavelengths of LED to see how much, what levels of oxyhemoglobin and deoxyhemoglobin in the blood, and in some cases other types of hemoglobin as well, but I'll talk about that in SpO2, such as carbon poisoning. If you've been in a fire, the levels of oxygen can be misconstrued. So there are ways of establishing what types of hemoglobin are in the blood using different wavelengths of light. Then there's so we've got the bottom image as well. So this is a thermocouple, and temperature changes induce a voltage change between the two different metals. So what are the measurement principles? We've got blood pressure. This can be measured both non-invasively and invasively, and it's associated with the pressure, as we established earlier, from the arterial blood vessels. Whilst the invasive method is more accurate, the non-invasive method is much more common, because invasive procedures require highly skilled people. They're not without risk. So if there's risk from infection, you've actually got to put a catheter directly into the arteries. So it's not ideal if you just want to perform a quick, simple procedure, which can be done by both skilled and unskilled people. So that's why NIBP is used very common. It's not as accurate, but it's got its advantages. There's 3 different methods. Now, primarily, we are only interested in the oscillometric method, which is the one that patient monitors use, patient simulation. You've also got palpation. This senses pulse and pressure at various places in the body. It's crude but fast in initial stages and emergency. There's auscultation. determining systolic and diastolic pressures through blood sounds in the artery, Korotov sounds, accurate but difficult to automate. So these are required to be performed by clinicians that understand the Korotov sounds, you know what to listen out for the sounds in the artery. Now the oscillometric method is automatic. It determines systolic and diastolic based on mean arterial pressure and the acoustic profile. Accuracy is determined by many factors such as leak, acoustics of the cuff, and tightness. And this is what we're mostly interested in for patient simulation. It's what we perform to test a patient monitor. So how does the oscillometric method work? So the method starts with occlusion using a cuff. As a cuff deflates below systolic pressure, blood flows, which is detected by vibrations in the arterial wall. So what a cuff is doing when it's first inflated is completely cutting off any arterial pressure within the point of measurement. So in this case, it's typically on your arm. You're completely occluding any blood flow, and then as the cuff deflates, the pressure within the arteries is starting to be able to overcome the pressure in the cuff. And your first major oscillation, this is systolic pressure. So if you've ever wondered how a cuff measures, it's measuring an acoustic profile within the arm, and it's using this to see where the first major oscillation is, and then it establishes, okay, that's systolic pressure. Mean arterial pressure is measured at the highest oscillation, so as the cuff is deflating further and further, the blood flow is starting to overcome the cuff, and then as cuff pressure starts to fall below diastolic pressure, blood starts to flow through the blood smoothly, and then the last major oscillation is observed, and this is your diastolic pressure, and that will be measured via the patient monitor. And it does this by, again, a transducer which converts these vibrational signals into electrical ones. So systolic, mean arterial pressure, and diastolic pressure. So when a greater accuracy than NIBP is required, this is where you'll need a real-time arterial pressure. So this takes a bit of time as well. That's another disadvantage with NIBP. As you've all probably had at some point, either used an NIBP cuff within clinical engineering, or you've used it on a personal, for personal reasons. If you've had your blood pressure measured, you'll see that it's not a real-time quick method. Whereas this, it's quick, it's got a higher degree of accuracy, but it's typically only used for surgical procedures, so when you're expecting a blood pressure to vary greatly. It's an invasive method whereby a liquid filled catheter is placed into an artery. Depends on which artery. Sometimes it's the radial artery, it could be the femoral artery. There's a few different arteries that can be used for IBP measurement, just to measure arterial pressure. Now the arterial pressure is transferred to the liquid inside the catheter and measured by the pressure transducer. So we went back to our pressure transducer slide to see how that's performed. And there's sensitivity. So it's typically 5 microvolts per volt per millimeters of mercury. Another sensitivity you might typically see is 40 microvolts per volt millimeters of mercury, but it's not as common for patient monitors. And if we go back to this slide here, the sensitivity is the pressure to the voltage. 5 microvolts per volt per millimeters of mercury. There's your millimeters of mercury pressure being converted to voltage, and that's being transduced by the patient monitor. SpO2 measurement. So to establish the oxygen saturation within the blood, to get that indication of how well oxygenated the blood is, the pulse oximeter relies on the different light absorption characteristics of oxyhemoglobin and hemoglobin at different spectrums of light. Typically 660 and 940 nanometers, but it ranges between I think 640 or 650 and 950 nanometers. It can be within any of these ranges for these two uses of LEDs. Now, a pulse oximeter can determine oxygen concentration by measuring the difference between red and infrared light being absorbed by arterial blood. So to do so, you use a finger probe, such as shown here, or an ear probe, but most commonly using a finger. And then a red and infrared spectrum LED is driven by the monitor. And this is done at consecutive intervals, as shown on this diagram. Typically, I think about 5 kilohertz, and this is shown in this image at a much slower rate. Just how the consecutive intervals are pulsed, and then there's this photo detector or receiver, and this converts the unabsorbed lights of red and infrared light into electrical signals. And it'll show on the next slide the graph of how light is absorbed differently by these two different wavelengths with oxygenated and deoxygenated blood. So using the receiver data, the patient monitor is able to establish how much oxygenated blood and deoxygenated blood is in the system. If more red than infrared light is being absorbed, there is less oxygenated blood cells. 100% SpO2, red over infrared ratio of 0.5, 82% SpO2, there's a red over infrared ratio of 1.0, and a 0% SpO2 ratio of 2. Now, why does more red than infrared light be absorbed when there's less oxygenated blood? This comes from the profile, so the absorption profile of both oxygenated and deoxygenated blood. The red light is absorbed more in relation to infrared light when passing through hemoglobin. So deoxygenated hemoglobin, we can see that red light is being absorbed more compared to infrared light. Whilst infrared light is absorbed by oxyhemoglobin, or HbO2, and this is your oxygenated blood cells. Now the ratio of at which light is being received can therefore provide an indication of the level of oxygenation. Now in principle, this translates to less infrared than red light being received, higher concentration of oxygenated blood, less red than infrared light being received, there's a lower concentration of oxyhemoglobin. And if you remember from the previous slides, about 940 used for the infrared LED and 640 for the red LED, and you can see the difference in absorption. This point here is known as an isopetic point, so there's a point at where the absorption is the same. So if you had an LED at 800 nanometers, it's not going to give you a very good data for oxygenated and deoxygenated blood. It's this variation in absorption between the two different wavelengths that gives you some data. Got ECG measurement. So we know that the heart is central to the respiratory system, and what it does is it converts these tiny electrical signals, also known as bioelectric pulses, to mechanical ones, so the ones for blood flow. It's not your electrical signals, it's your blood flow, which is crucial for establishing how well the heart is performing. Now these tiny electrical signals from the heart are amplified, measured and displayed on the screen. ECG machines may typically use 3, 5 or 12 lead configurations. Cardiac conditions or arrhythmias that can be diagnosed using ECGs include abnormally fast heart rates or tachycardia, abnormally slow rates, bradycardia, ischemia, which is a restriction in the blood supply to a part of the heart, an acute myocardial infarction or blood clot in the heart. Now, clinicians, experienced clinicians, they can look at an ECG monitor, they can look at tiny little anomalies within the ECG, and they can quickly diagnose a condition that they might suspect. So they're really crucial measurements and why they're part of the main vital signs. Again, just got the image that shows the normal sinus rhythm, where the P wave is generated during atrial depolarization, and then your QRS complex with the ventricular, when the ventricles are depolarized, and then the T wave representing the return to resting. And something that we highlight in the defibrillation webinar is that the T wave is the most sensitive part, or the most vulnerable part for defibrillation or pacing. So it's really important how defibrillators monitor the heart wave and when they're going to output a pulse if there's electrical activity. It cannot pulse during this T wave. And the way it does this is it looks for a QRS complex. If it detects a QRS complex, there's only a time delay when it can then produce a pulse. So it must perform within a very short delay after detecting the R wave. Placement of the ECG leads is standardized, so the interpretation of the ECG is consistent. It's one of the most referred to means of measuring the electrical potentials by looking at the position of electrodes. It's taught very often. It's known as limb leads, and this is the shown on the patient here in a triangular shape, known as the Einthoven triangle. So you've got left leg, right arm, left arm, and these limbs can sometimes be referred to as different things, but you'll see that there's standardized configuration of where ECG leads need to be placed. C1, C2, C3, C4, C5 and C6 are placed across the ribs for further diagnosis. You've got your free lead ECG, which is typically RA, LA, LL. But then you might have a 10 lead ECG, which uses all of the ECG connections. Okay, so there's several ways of deriving respiration rate from the ECG leads and signals. Most commonly used is the measurement of the transthoracic impedance between the ECG leads, i.e. lead 1, lead 2 or lead 3. So lead 1 is RA to LL, RA to LA, lead 2 is RA to LL, and lead 3 is LA to LL. The thoracic cavity expands inspiration, the impedance of the chest increases, whilst during expiration the thoracic cavity reduces in volume and therefore decreases its impedance. It's a very simple measurement. You've got a baseline impedance, let's say across the chest, say we're measuring a baseline impedance here, and it's 500 ohms. During expiration, it might be 499 ohms, and then during inspiration, at peak inspiration, it might be 501. So you might only have a variation of 1 ohm, 2 ohms, but that variation is measured by the patient monitor, and it measures respiration using the ECG leads attached. In any method, the ECG leads are placed on a human chest as shown above. Respiration rates can be monitored through all limb and augmented leads. Most monitors and recorders allow a selection of leads. Now there are other ways of measuring respiration using the ECG leads, and that's by looking at the change in ECG amplitudes, and that's as a result of the change between the position of the electrodes. So it looks at the difference between the changes in the position of as the way the heart moves. So it looks at actually the amplitude of ECG rather than resistance, but I won't talk too much about that one. This is the most commonly used respiration measurement, and this is how we simulate this vital sign when testing. So this is the most common method, and it gives you a better idea of how simulation is performing. Simply, if you look on any patient simulator, you'll see that it's got a baseline impedance, and it's got the variation impedance as well, which can be changed typically between 0.5 ohms and anywhere up to 5 ohms normally. Then we've got temperature measurement. So the most common temperature sensors used on patient monitoring systems are these thermistors. Now there's two types of thermistors. Negative temperature coefficient, as shown here, NTT values. This means that the resistance decreases when the temperature increases. This is in reverse there, so as temperature increases, your resistance is decreasing. And this is most commonly used on patient monitors. YSI 400, again, 9 times out of 10, you'll be seeing this in the service manual of a patient monitor. YSI 400 is most common, but there's also YSI 700, which contains a dual element. But that's the reason YSI 400 is used and most commonly used in the medical industry is that it's more accurate over the ranges you'll see for body core temperature, which I think is 0 to 75 degrees Celsius, whereas YSI 700 standard is a much wider range. It goes to minus 25 degrees C up to 100 degrees C. So it's got a wider range of accuracy over those limits, and that's why it's not as commonly used as YSI 400 is. So what you typically, although I always check the service manual of the manufacturer, but most times you're going to see negative temperature coefficient thermistors using YSI 400. Now, of course, they might not use this type of measurement. They might use a thermocouple. They might use PTCs, and they also might use a different standard. So in that form, it can be quite convoluted. But it will be specified, and you're most likely going to find it's going to be this type of thermistor here, this type of thermistor value. And to simulate, which I'll probably repeat myself a bit later on, you're just using resistance set values. So if you want to simulate 41 degrees, you're going to use this resistance here. And if you want to simulate 25 degrees C, then you're going to use a resistance of this value. And quite often a patient monitor service manual will just specify a resistance rather than a temperature. Okay, so performance testing. Patient monitors are very comprehensive devices. They're multi-function monitoring equipment. So there's not just one standard that needs to be followed. It's not like other pieces of equipment that you'll find in healthcare. There's multiple standards that need to be followed. Now, IEC 60601-2-49, that establishes the basic safety and essential performance of a patient monitor, but it does not specify the requirements for individual monitoring functions. It addresses multifunction patient monitoring equipment as a system. Performance verifications are broken down by individual function and categorized into different standards. And here's a couple of examples of these standards down on the right too. For invasive blood pressure monitoring, it's got its own collateral standard. Electrocardiograph performance, again, it's got its own standard, and so on and so on. Okay, so visual performance and safety tests are required. So typically 2 test instruments are required. A typical PM is as follows: electrical safety tests. And what you're going to need for this is an electrical safety analyzer for measuring your patient leakages, your earth leakages, enclosure leakages, etc. Depending on what standard you're using, it could vary the terminology. Then we've got visual checks. wiring interface connections, enclosure, inspection and replacement of consumables, cleaning and sterilisation, alarms functioning correctly. And for this, you're going to need disinfectants, cleaning tools, consumables, and labels. And finally, performance tests. You're going to need a patient simulator. Patient monitors are also regularly tested in situ. This is why multi-parameter patient simulators are often preferred in the field. So the image shows how PM could effectively be carried out using two portable instruments, alongside a couple of other tools such as labels, cleaning products, etc. Something we've done at Rigel as well, we've got a rucksack. It's like a strap bag which can easily hold these two testers, and then it's got a small port at the top so you can have your disinfectants, cleaning tools, consumables and labels. So that particular bag that we sell is ideal for testing patient monitors for moving around within a hospital. So performance tests, also referred to as quality or functional tests, typically executed using a patient simulator across a number of applications. And they're all part of an acceptance test, preventative maintenance cycle, or repair. Now, a typical test cycle for a vital signs monitor might include integrity testing, so leak and overpressure testing, parameter accuracy, printer checks with speed and amplitude, alarm checks, pitch, frequency and volume, physiological simulations, dynamic simulation. Cardiac or performance waveform generated with preset amplitudes and frequencies. Normal sinus rhythm, arrhythmias, performance waveforms, pacer waveforms. So to test ECG, we're simulating multiple arrhythmias, just electrical signals. Basically, if you're talking about from an electronics point of view, it's a signal generator. Testing ECG, it's an accurate signal generator that replicates all the different waveforms. So why do we test ECG? Well, we know that it's important for analysing a patient's condition. We need to ensure that the input circuits of an ECG monitor are able to measure these really small, tiny electrical signals accurately. And also, patient monitors have software that's able to interpret these signals to the corresponding conditions. You'll see that when you perform a simulation, it will then the monitor will quickly establish that a condition has been detected, a type of arrhythmia, and then it's a way of testing that the alarms work. So if a condition is alerting the clinician, does it have the right pitch and amplitude? Because clinicians use these pitches and amplitudes to quickly monitor a patient's condition. So QRS beep, the pitch and frequency, the alarms, high and low alarms, alarms for disconnected electrodes, how well the arrhythmia is recognised, the sensitivity test to gain change, the zero offset, the isoelectric line, frequency response, and printer calibration. So all these things are crucial for patient monitor's performance. So how do we test it? Well, most ECG simulators have multiple arrhythmias. The PatSim 200, for example, has got over 40 selectable arrhythmias with on-screen waveforms for quick visual comparison. So you can look at this, compare it to the on-screen waveform of the patient monitor, and quickly establish if the patient monitor is measuring correctly and giving you the right waveform. In this example, we've got atrial flutter, and it shows how it compares to the electrical signals of the heart. It's characterised by this re-entry loop in the atria, and it causes the atria to beat at a rapid rate. The ventricles limit the trigger, so it's getting multiple triggers, but the ventricles are actually limiting this. So as a protective measure, it's limiting the trigger and how many QRS complexes are being generated. And that's why you see this periodic QRS complex between this loop in the atria that's shown here, demonstrated on screen. So ECG simulators normally output a normal sinus rhythm as standard. Normal sinus rhythm is a result of just regular, normal intra-electrical impulses within the heart behaving as it should. Simulating other ECG arrhythmias ensures that correct electrical activity of the heart is being measured. For example, ventricular fibrillation, or ventricular fibrillation course in particular, is chaotic electrical activity in the ventricles. Now, coarse and fine VF have very different outcomes. Defibrillation from VF coarse to normal sinus rhythm is more favourable than VF fine. Now, greater than 3 millimeters in amplitude on printed paper, that's the difference between VF fine and VF coarse. If it's greater than 3 mil VF coarse, it's less than 3 mil VF fine, and that's why amplitude and gain change is crucial when testing patient monitors. So what happens within this particular type of arrhythmia is that coarse will gradually reduce from VF coarse to fine. VF fine is identified as less than 3 millimeters of amplitude, and this is what will progress to asystole if left untreated or flatline. And this particular type of arrhythmia is unfavourable for defibrillation. Once you get to this point, your chances of survival are greatly reduced. And this highlights why gain change and printer checks are crucial. So one of the crucial points for measuring. That brings us on to performance waveforms, because quite often these performance waveforms are used to check the printers. So there's a variety of waveforms, again much like signal generator, sine wave, square wave, triangle wave, sawtooth wave is another one. Square wave performance wave is ideal for testing amplitude on an ECG printer. Now a QRS complex, a standard NSR wave might not be ideal for testing the small printouts on the paper, whereas square wave will give you a very clear indication of the peak-to-peak amplitude. But it's always worth referring to the manufacturer's service manual if you're unsure of what tests are required. NIBP testing, so oscillometric pressure simulation, adult neonate simulations, the performance of the algorithms which calculate the systolic, diastolic and mean pressures. So they're tested in real life conditions, simulated by the patient simulator to the patient monitor. Got pulse volume adjustment, custom static pressure test. Now it's important to note, because we get the question a lot, that static pressures are useful for verifying the performance of the pressure transducer and verifying the integrity of the tubing, whether there's any leaks, but also the accuracy over a range of pressures. Dynamic pressures are not used for testing accuracies of the internal manometer, as it's a dynamic simulation. You'll find that a patient monitor will have a range of static values for testing its internal manometer, and that's your accuracy of measurement. There's system link pressure, system overpressure, there's also digital monitor. These are the type of tests that are included. So a leak test will verify and ensure the integrity of the pressure system, including the cuff and the tubing. The system overpressure, this is like a protective measure, ensures the system is able to vent when pressures reach a value that could harm the patient, exceed a safe value. So why test an IBP? A leak or a cuff in the pressure system. There's an example here of how a leak test is measured over time, and it must fall within acceptable values as specified by the manufacturer. So this again will be within the service manual. It might specify a start pressure of 160 millimeters of mercury and a pressure drop of, say, 5 millimeters of mercury over 2 minutes. That's just an example. As long as it falls within those values, then it's within specification. So you must refer to the manufacturer. And the pop-off test is produced by the patient simulator, where a value is increased until the vent within the patient monitor allows the pressure. So it's a safety measure. So the overpressure valve, we're also known as the pop-off valve. We've got dynamic pressures and static pressures. So the static pressures, as explained before, they test the linearity over a set point of ranges. So it might be 300 millimeters of mercury, starting at 50, 100, 200, 300, for example, testing a linear range of pressures. Dynamic pressures, because manufacturers of automated NIBP monitors use different algorithms to determine systolic and diastolic pressures. This is known as pulse volume dynamics. Testing IBP. The static pressure test is useful for verifying the performance of the pressure transducer. It's used to test the accuracy over a range of pressures. For example, again, a manufacturer may say a static pressure linearity test of the following pressures: 250 to 0 in 50 millimeters of mercury steps. Again, you need to refer to the manufacturer's service manual for service or calibration modes for this test. Dynamic and static. So the static pressure tests are useful for verifying the performance of the internal transducer. A linearity test can be done similar to that of NIBP in order just to verify that the accuracy of the monitor over a pressure range. The accuracy of the pressure transducer can also be verified using a dynamic pressure simulation. Now this is direct measurement, remember, so it's going direct to the monitor. It's using electrical signals to simulate. Why test IBP? Pressure transducer performance, static pressure linearity, alarms, dynamic pressure, so hypertension, normal hypertension. And we've got SpO2 testing. Optical SpO2 simulation fingers allow testing of the complete system, such as the Rigel pulsar. We're using a digital finger, to test the complete system. Most pulse oximeters on the market are capable of measuring under extreme conditions. So it's important to understand that you need to establish the correct operation of those conditions. This is more favourable than going direct to the monitor because it verifies the performance of the monitor as well as the SpO2 probe and its connection cables. The digital finger provides variable attenuation to light in the red and infrared wavelengths. It verifies the performance of the monitor measurement circuits and SpO2 characteristics by simply displaying the SpO2 percentage value and the heart rate on the monitor. So why test SpO2? Faulty probes, LEDs degrade over time. You might have non-OEM probes, so there'll be a deviation in wavelengths. Sometimes there's crossover between the connections of the SpO2 probes, so it can be easy to get some crossover again between the probes that are used. There's contaminated lenses or probe windows, damaged wiring or patient cables, inaccurate calibration of the SpO2 monitor itself, testing of the audible alarms, display of plethysmograph. So overall, these tests are to verify the performance of the monitor measurement circuits, the SpO2 probe characteristics to trigger any alarms. They also ensure that the monitor can accurately measure different pulse volumes. Probes are also consumables, so they can suffer wear and tear, they're easily replaceable, so it's important to test the functionality of each probe. So how to test SpO2? Pulse oximeters detect the change in light absorption. Oxygenated and deoxygenated blood absorb red and infrared wavelengths differently. The red line shows the fully oxygenated hemoglobin, 100% SpO2, whilst the blue line shows the fully deoxygenated hemoglobin, or 0% SpO2. So around the, we know that the 800 point is your crossover point where it's the same. SpO2 is calculated by looking at the changes in absorption, or A, at wavelengths caused by the variation of blood volume in pulsating arteries, where R, absorption of the red in the AC component, so the AC component is your pulsatile component, which is this point here, which is being highlighted now, over the absorption of red in the DC components. This is your non-pulsatile, things like bone, skin, tissues, things that aren't changing, where the absorption isn't changing. Now the pulsatile light is where the ratio of ratios comes in. So this is your pulsatile red over infrared light, and that difference in absorption is what gives us our R value, and this correlates with SpO2 saturation. And the R value is important when it comes to pulse simulation, pulse oximeter simulation. So when pulse oximeters are developed, the ratio of absorption at red and infrared wavelengths is calibrated with direct arterial oxygen saturation measurements. So it's a very accurate form of measurement. Each R curve is therefore different and manufacturer specific, which is why our SpO2 simulator is customizable R curves. So these are your R values, which are from the ratio of ratios, and at different wavelengths, you've got these different variations in slight variations in wavelength data. You've got variations in data, and that's highlighted in this screen. So there's two examples of different manufacturer specific R curves. There are slight deviations in their interpreted values. So for each SpO2 device, each manufacturer, to get more repeatable results, you may need to use an R curve that's either available within the UNI-SiM, or there's customizable ones as well, which can be created by the customer, by the client. It can be done in-house as long as it's verified by 3 different monitors. And then there's respiration and temperature testing. So in this example on RA to LA, lead 1, 5 to 180 beats per minute, does this using the delta resistance over a range of base impedances. So kind of as explained before, that the simulation is performed using this delta varying resistance. Could do apnea simulations, whereby we've got no breaths per minute. So why do we test it? Linearity of respiration rates. It's normally between 100 beats per minute and breaths per minute, and 0. So I put BPM, but it's breaths per minute, and 0 sleep apnea. Appears on the monitor as an absence of breath. Alarm should sound if breaths are too high, too low, or during sleep apnea. Testing temperature. Simulating thermistor temperatures for a set number of resistances. Temperature sensor is either YSI 400 or YSI 700. But as explained before, you're typically going to see this 9 times out of 10. It's done this fairly simple method. In theory, you could use a decade box, and you know that has been done in the past. Same with cardiac output. You're just using simulation of the resistances, and that's how to test temperature. Very simple method. And that brings us to the end of today's presentation. Again, I'd just like to highlight, in case you missed the beginning, that we've got a PatSim 200 competition, which you can win for free just by filling out a quick questionnaire on vital signs. This helps us develop what we're doing right with our patient simulators and how perhaps we can improve in the future on our current products for patient simulators. So it'll only take, I think, 4 minutes to carry out, and you'll have a chance just to win a free patient simulator, the PatSim 200. If you did miss the first slide, it will be available in the handout section. Win a PatSim 200 PDF, and there's a QR code or a website link there for accessing that survey. We've got a demonstration coming up within the next few weeks. In 2 weeks' time, on the 14th of December, for a demonstration using a PatSim 200 and a UNI-SiM on a patient monitor, how you perform performance tests on a patient monitor. So if you've got interest, please sign up to our next webinar, that's in 2 weeks' time. But if you've got any questions for today's webinar, pop them in the chat box or question box below, and I'll get back to you as quickly as possible. If you weren't able to highlight CPD on the form, or you missed it, and you do wish to receive a CPD certificate, also let me know in the chat section below, and I'll add you to our system manually. Just bear in mind that there's an attendance and whether the presentation has been your main viewing browser, basically. So it's done automatically. Unfortunately, if you don't fall under those criteria, then the certificates are not issued. So it's important to highlight that for any future webinars. You need to have a certain level of viewing and attendance as well. So just so you're aware, for any future webinars, if you don't receive the CPD certificate. But that brings us to the end. Yes, if you've got any questions, pop them in the chat box below. Thank you for viewing today's webinar. If there's anything I can be of help, just pop it down below. Okay, thank you.